Okay, great. Thanks very much. So this is my, I'm going to be talking about meta-analyses for today's EBM session. So it's going to be very interactive, and I really hope that people will pitch in, because there's a kind of quite a lot to get through, and I could really use your help with this. So Rafa sent the article around. This is the one that we'll be looking at today. I don't know if anyone's had a chance to read it or look at the abstract or anything, but it's a very big meta-analysis. It's actually sort of 4 meta-analyses in one. So we're just going to focus on one aspect of those and focus on the actual methodology and statistical side of it. So it is looking at corticosteroids and the risk of death within 28 days for patients with severe ALK-HEP compared with pentoxifylline or placebo. So just a quick kind of clinical summary. Alcoholic hepatitis is a syndrome that arises after the liver is injured by excess alcohol intake. I suppose you may say any alcohol intake is excess, but I mean, for a diagnosis of clinical alcoholic hepatitis, that's usually about 40 or 60 grams of alcohol a day for more than 6 months. So that's a fair amount of alcohol with kind of ongoing use. There's some diagnostic criteria here. It's a kind of a complex diagnosis to make, but generally the hallmarks are jaundice, a liver enzyme rise, mostly AST, and then there are some pathological changes, like histopathological changes as well. Generally speaking, it's a fairly severe condition with a pretty high mortality. And early 28-day mortality can approach sort of 60% in patients with severe alcoholic hepatitis. So clearly something that needs to be kind of addressed and treated well. So the treatment, I mean, this is what was known for a long time about alcoholic hepatitis, is that treatments focuses on alcohol cessation. That's the most important thing. Nutritional support is important as well. And there are some other medications that can be used. So that's kind of steroids, pentoxifylline, N-acetylcysteine, and G-CSF were kind of being investigated. So we're going to focus on whether steroids and pentoxifylline actually have an effect in ALK-HEP. So kind of first question for you guys, what actually is a meta-analysis then? Can anyone just give me a quick kind of summary or your thoughts on what you understand by meta-analysis?
Looks like a collection of
comparing several studies.
So I heard several studies. Yeah, that's.
No, I was saying it's like it's a study design that involves going through multiple studies and then comparing them, and then like sort of making conclusion out of all those studies together.
Yeah, exactly. That's pretty much it. So exactly. So it kind of uses numerous underlying, So it's a synthesis of individual study results. So the key point is it relies on existing data that's already been gathered in other studies. So it doesn't generate any new kind of data that isn't already out there, but you may find new kind of information or new conclusions based on data that already exists. So the idea is to get a single estimate of a treatment effect based on it, particularly in a situation where you have lots of studies, each of which individually isn't powered enough for you to find something significant. So usually the situation is you have numerous trials with few patients, and then you don't find an effect. The question is, did you fail to find an effect just because you didn't have enough patients in the data? So this kind of summarizes information from lots of different studies. The key point, as you said, is that it's entirely dependent on the underlying study. So if the underlying sources are biased or there's serious flaws in the underlying work, then actually that will be reflected in the meta-analysis, and so the conclusions won't be as strong. There's usually 5 standard steps when you're trying to do a meta-analysis. So step 1 is always, with any kind of clinical research, is you have to state your research question a priori before you've actually started out doing the work. So what is the question that you have? Number 2 is then performing a kind of literature search, which has to be comprehensive and has to be reproducible for anyone else who wants to come and try the same thing. And the idea for that is that obviously you want to include the maximum amount of data so you have the most stuff to work with. But there's also an important part of doing a very comprehensive review, because you want to try to avoid publication bias if possible. Can anyone explain what publication bias is? And you can feel free to refer to the chart I've helpfully placed on the right of the slide.
When I believe when all all the studies have, for example, like this positive effects, but the other study that they were with negative result, they were not published. So we will only lift up with those studies that are with positive, for example, results, I guess.
Yeah, you're kind of getting it, Noah. So it's this, you're kind of, so what you're saying is that the risk of, or the chance of a study being kind of published or out there depends on what the study finds. And that's a problem, because if you only publish studies that have positive results, or kind of what you might think is an interesting result, then you may actually miss the true effect of something, which may be very minor. So can anyone talk me through the funnel plot? Does anyone understand what this plot is on the right-hand side? So if you a funnel plot just is a way of looking for publication bias. So on the x-axis, you've got the effect size that the study has published. Each of these red points is a study. So it's not an individual patient. It's it's the study itself. So the studies are the unit of kind of observation in meta-analysis. So the effect size is what, for example, your odds ratio is for a treatment. And the further you go from the middle line, the more significant the effect size is, either in a positive or a negative direction. So this first graph shows that the studies, each study, there's like an equal number of studies on either side of the effect size kind of line of the kind of line of unity, which is the middle line that shows there's no effect. So it's a nice and symmetrical funnel plot, which means that studies are equally likely to be published, whether they show a positive or a negative effect. That's in contrast to the one below, which you can clearly see there are more studies being published on the right-hand side. So studies that are that are finding a positive effect are being published at a greater rate than studies that are not. So that suggests there's probably some publication bias, because in the kind of natural state of things, if you investigate something over and over again, you should get a kind of an equal distribution of estimates around the true effect. So if that's not happening, that means there's publication bias, and that's something to kind of look out for in a meta-analysis. So just going back to the steps. So step number 3 is to extract all the data from the study. So you have to screen all the studies that you've got in your literature review, see which of them you want to include, and we'll go through what happened in this paper in a second. You want to evaluate the quality of the studies and the sources of heterogeneity, and we'll go through heterogeneity again in a few minutes. Then you do the actual bulk of the analysis, and you estimate your one kind of summary effect for that treatment based on the information that you have. And then finally, you kind of state your heterogeneity, publication bias, and try some sensitivity analyses, and we'll go through those things as well. So this is the title of this meta-analysis. So this is step 1, so stating the study question a priori. Just based on the title, can anyone come up with a PICO statement about what the study question is? So PICO statement, just to remind you, is patient population, the intervention, the control, and the outcome that you're looking at.
I believe.
So the population is people with severe alcoholic hepatitis.
Yep, great. Do you want to carry on, Patrick? Do the rest?
The intervention will be basically like giving corticosteroids, comparing patients with alcoholic hepatitis. Yeah, comparing patients with alcoholic hepatitis, there will be a part that will receive corticosteroids versus, and they will compare with pentoxifilling and placebo. And,
Yeah. Yeah.
And then the outcome will be mortality, reduction in mortality.
Yes, exactly, or just mortality generally. Yeah, exactly. Right, so that's pretty much it. Let me just, so patients with severe alcoholic hepatitis. So in this study, just to expand on that, they defined severe alcoholic hepatitis as patients with a MDF is Madry's discriminant function. That's just a score of severity of alcoholic hepatitis that you kind of should calculate for any patients admitted with alcoholic hepatitis and or encephalopathy. Intervention and control, so steroids, pentoxifylline, placebo, and various combinations. We'll go through those in just a second. And the outcome is 28-day survival. That's kind of what we're going to focus on. This paper is actually much bigger, and they also looked at longer-term survival, so 6-month survival and treatment response using something called Lille score. But I think we'll just focus on the kind of the use of steroids in short-term mortality in alcoholic hepatitis. So that's our study question. So then they went and did literature search. They found 11 studies that they wanted to include. They stated their inclusion criteria a priori, and they said they wanted randomized control trials only. They wanted studies that were published in English only. They wanted studies with kind of full text publications, not just abstracts. And the final thing is they said they needed studies, control trials whose principal investigators agreed to participate, and that's something they stated. So what do you guys think of those kind of inclusion, exclusion criteria? Do you think those are fair, or do you think there's any sort of maybe questions or red flags you have about those?
I think this is fair. For a meta-analysis to be, one of the things you assess is homogeneity, how homogeneous the studies are.
Yeah.
So they need to have quite a narrow, quite a tight selection criteria.
And also, like studies that may be published in English may mean that geographically, that means the population may be in only English-speaking areas. So you don't know, like if the same, whatever you got, whatever results you get from the final outcome can be applied in other countries because you didn't get that population.
And they actually.
Oh, yeah, so that, well, yeah, what I meant is the generalizable. Yeah, that's what you mentioned on the chat.
Yeah, right, exactly. So kind of really great points, actually, precisely. So that was what I thought as well. I think only including RCTs is fair enough. I think that, you want a high quality study. Including only full text publications is also fair enough because, abstracts you don't just have enough information to work with. It was a point about studies being published only in English. Now, although studies done anywhere in the world can be translated into English, and English usually is the language in which medical literature is published, there is a risk of that. So I think those are great points. And this thing about only including studies whose PIs agreed to participate, I think that's something a bit odd there. Why would you not agree to participate in a meta-analysis of your randomized control trial? What are you, not to cast aspersions on anyone, but what are you trying to, is there anything that you're trying to hide, or I don't know, it's just a kind of a question that you have to bear in mind. But of course they had to exclude those because it's not really possible to do a meta-analysis if people refuse to give you access to the data from the studies. So for this study, that they tested all these various combinations of things. As I said, we'll focus just on the steroids versus placebo control for our work, but they also checked steroids versus pentoxifylline in these kind of combinations and pentoxifylline alone. So this is your table one, which is, so just to kind of zoom out a bit. So you've now got the studies, you've extracted the data, and now you're doing the analysis yourself. So this is your table one for this meta-analysis. So this is just a statement of the patient population. again, so focusing just on the stuff in the red box. So this is looking at steroids versus control for this group of patients. What do you want to look at in table 1 generally? Just quick points. I think this is something that we should be familiar with now. What do you want to make sure about between the two arms?
Matching characteristics, maybe.
Yep. Yeah, are they balanced exactly? Anything else?
A number of patients in each arm.
Yeah, great. Also, you know, is this a kind of a population that's relevant to you? You know, is it this kind of age range, the sex distribution, the severity of patients? These patients had the last one is the Mandatory Discriminant Function score. That's a fairly high score. So pretty severe alcoholic hepatitis. So yeah, exactly. These are balanced. And remember, you don't want to see p-values in table 1 because that doesn't necessarily, it's just as complicated. So yeah, that's important. Just make sure they're balanced visually.
If I can just point on one thing in relation to the previous slide.
Yes.
Can you hear me? The previous one, like the slide just before this.
Yeah.
So when it mentions RCTs whose principal investigators agree to participate, I think what they meant is that you can do two types of meta-analysis. One which where you get the aggregate data, and one where you actually get the patient data, which was used in the individual RCTs.
Yes.
So when you want a patient level data, which probably is what they have used in this particular one, based on the first table, I think you need the principal investigators to participate. Otherwise, you won't be able to get the patient level data. You can only get aggregate data. That is what I think they meant by saying whose principal investigators agree to participate.
Yeah, you're completely right. Exactly. So that's exactly what it is. So, right, meta-analysis can be done either just by looking at the summary statistics of the studies themselves and not looking at the underlying data yourself, or actually looking at the data yourself and combining all of that stuff in your own analysis, which is a stronger way to do a meta-analysis, which is correct. That is what they did here. But as you say, obviously you don't have access to the data if the people won't give it to you. So just the question is, you know, why would those PIs not want to share that data in the name of science? You know, like what is it that they don't want to share that for? So I think it doesn't invalidate the study. It's just something I think you should just bear in mind that this there is potentially some bias in this, that only people who wanted to share data had their studies included in this analysis.
Mantej, how did they do a meta-analysis when they only had one RCT in the last?
Yeah, that's a great question. So there was another one. I didn't display it very well, but there was one RCT that did various things in combination. So there's actually at least two. But you notice something that I will come back to later, because something doesn't quite add up when we get to the later part of the study, but we'll come back to that. Okay, so then comes the actual meta-analysis. So as Subrat was just saying, this was a meta-analysis of individual patient data. It wasn't just combining the summary statistics of each study. That's a much easier thing to do. You take the effect estimates of each study, weight them, and then come up with a summary estimate. A more robust way of doing it is to extract the individual data from each of those studies and analyze it yourself in one big group. They did an intention to treat analysis. I think people have can someone define that for me again?
Basically, basically you respect the initial randomization of both arms in the randomized trial.
Yeah, exactly. Yeah, so you analyze people based on the treatment they were assigned to, not what actually happened in real life, because so many things could happen along the way. That's in contrast to a per protocol analysis, which is when you only account for people who have actually received the treatment that you wanted as per the protocol. So intention to treat analysis, which is again the more robust way of doing it. They left this statement in the methods. They said the risk of publication bias cannot be statistically assessed because of the number of trials included per meta-analysis, which is a little bit to your point, Patrick, that there's so few trials actually included, which is actually not an uncommon problem in meta-analysis, that they couldn't really determine whether there's publication bias or not because there were so few studies. But they didn't actually show even a funnel plot, just even graphically. And then there was this line in the methods. So the line, this is the kind of point to which I think there's often these opaque seeming statements in meta-analyses that kind of frighten people. So Cox Proportional Hazards regression, including trials as a random effect, was how they analyzed this data. So we'll just talk about that in a second. And they also said separately, they used a model with fixed effects stratified by trial. So you were talking about heterogeneity earlier on, Patrick, heterogeneity, homogeneity, and you know, how these things can be studied and modeled, and they're very important. So what actually are fixed and random effects? Because does anyone know what it is or have any thoughts about what they might be? Just based on the name.
You also have some clues, graphics in front of you that you can use.
Yeah.
Point.
It's also just stated on the slide, but yeah, I mean, we can talk through it because I think it's pretty complicated, and it's important to, I think, understand for this purpose. So when in a fixed effects model, you're assuming, so in the graph here on the left-hand side, can you see my cursor, by the way? Yes. In the graph, the gray distribution is what the underlying effect is that you're trying to measure. Remember, in any study, there is some real effect in nature that you're trying to get at based on, and you're trying to estimate what that is using a study. You obviously can't measure the entire population, so you take a sample, and each of these things is, each of these smaller graphs in blue, yellow, and green are the individual studies. So there you're saying there's one underlying true effect of, for example, the use of steroids in ALCAP in all populations, in all people. In a random effects model, you're saying there is no single true estimate because things vary based on population, patient severity, there is heterogeneity within the studies. So there is actually a distribution of underlying effects that depends on whatever other factors, and each study is sampling from what is a different distribution. So there is some heterogeneity in the study, and that's giving you this kind of random effect. I don't know if anyone is able then, just with that explanation, in what situation would you expect both of these models to give you exactly the same result?
Can you repeat the question?
So if you're doing a fixed effect model, so you're saying that you're doing one analysis where you're saying there's only one true underlying effect amongst all the populations that you're studying, and there's the only difference in study outcomes is because of the way the studies were kind of performed. In a random effects model, you're saying there's lots of different effects. So steroids will work in alcohol hepatitis, say for men, but not women. And then each study is getting an effect estimate based on each of those individual populations that they're studying.
I think one of the ways to look at it, Mantej, if I can join in, is that to answer the question, it would be the same if you have good homogeneity, like the heterogeneity is low, because then you have all of them under the same curve. And also, I think the way this estimates are made is with an assumption that if the population, I'm not talking about the sample, if the population follows a normal distribution curve for an effect, and if you draw enough number of samples of different size, that also follows the normal distribution curve. That is the whole idea behind the fixed effect model or the random effect model, that if you draw enough number of samples of different sizes from the population, the mean effect of that each samples would follow a normal distribution curve. And that's what is being is expressed as mixed effect models. And we're saying that with this normal distribution curve of the different samples, we're estimating with a certain certainty, like for let's say 95% confidence interval, that we are actually measuring the effect of the population. Is that correct, Mantej? Like, I think that's what we understand from the fixed effect model.
Yeah, kind of. Yeah, I think your kind of first point, you answered the question correctly, that the situation in which these would yield exactly the same results is if there is zero heterogeneity between kind of the underlying studies and everything is just one population, which is a very artificial scenario. And as for your point about the drawing from the distributions, I think, yeah, I think you're describing the central limit theorem, where you have, where if you, I think it's, I think it's more, that's more the description of the central limit theorem, where saying if you keep drawing samples from a distribution, eventually you will form a normal distribution around the true estimate. I'm not sure it's directly the same as fixed and random effects, but maybe we can, we can talk offline, as they say, maybe, so just so we don't get kind of bogged down in it.
Yeah, because I think the main thing is what, I guess, like the one point that I would want everyone to understand is what was said in the beginning by Surya, but also what was written by Francisco. If that's correct, Mantej, just so that I don't overstep you too, but I think that that's reasonable at that level to understand, like, what's the difference between fixed and random, and when you understand when the situation would be the exact same result. So I don't know if you read what Francisco wrote as well.
Yeah, just reading it now. Yeah, exactly. So, exactly. So, exactly. If heterogeneity, so it's about how heterogeneous the studies are, and I will explain that in a bit more detail going forward. But just wanted to explain how this analysis, because you see lines like this in meta-analyses, and then it can be frightening. So, the summary is, it's more robust to use a random effects model because that's much more like reality. So then the first thing was Cox Proportional Hazards is the model they used. Just what is a Cox Proportional Hazards model? Does anyone know this? Or what is a hazard? What is, how would you compare the amount of death in two groups of patients? One who's receiving steroids and one who's not.
Hazard ratio.
So what is a hazard ratio now?
It can measure like how much an intervention would like positively or negatively affect the patients, I guess. I'm not sure how to like
so I can jump in and try it out. So hazard ratio is you measure the probability of that event happening to your control group relatively to the other arm. So for example, if it's more than one, then it's most likely to happen in your group. If it's, if the ratio, if the variable includes one, then it's not significant. And if it's less, then it's less likely to happen on your treatment arm comparing to placebo.
Yeah, I think, yeah, right. So I think you got it there. Is that a hazard is the probability of the event occurring within the time that you have specified. So there is a time component to it. A hazard ratio is when you compare those things between two different groups. I'll just give all the answers away here, but so yeah, right, exactly. So between two different groups of people, and the key point is that when you take a hazard ratio, you eliminate the time component from that equation. So what you have is a hazard ratio. It sounds kind of, it's the instantaneous rate of the event occurring. So the power of that is in saying if a hazard ratio of death, for example, between two groups is 0.5, what you're saying is at any point, kind of in perpetuity, at any point, that second group is dying at half the rate of the other group. So that is the strength of a hazard ratio, that it kind of, you're not limited to kind of time-based statements like relative risk and odds ratio. So that's a very useful way to measure survival analysis, to do survival analysis. A proportional hazard, just to kind of move on, is so you're assuming that the hazard is proportional the whole way through. The hazards are not changing. That's one of the key assumptions, that in the group getting steroids, for example, they are always forever going to die at less than the rate of the people who are not receiving steroids. So that's one of the key assumptions. That's obviously never going to be the case in real life. There will always be things that change that relationship, but that is one of the key assumptions of this model. And why do you need this kind of model? Why would you need this rather than just looking at survival curves, for example, of like numbers of patients who are dying between two different groups? It's here. I mean, it says important to adjust for confounders. So what kind of confounders would you want to look at? What other things could cause death?
Would that be things like comorbids, if someone has liver disease from any other condition outside of alcohol use disorder?
Yeah, exactly. So anything else that will impact your outcome, so age, comorbidities, baseline characteristics, all this. So you need to adjust for those things whenever you do an analysis. So that's why you need a model like this. You can't just have survival curves when you're trying to understand the effect of something like an intervention on survival. So moving on to the results of the meta-analysis. So it's a big table. Is this familiar to people from looking at meta-analyses in the past, this kind of layout? If it is, can someone just talk me through, what are we seeing here?
So I think the size of the box represents the number of participants in the study. The length of the line represents the difference in standard deviation, and then where the box is the mean. And then that central line, so for example, if it crosses that central line, it is not statistically significant because the standard deviation is on, it crosses 1.
Yeah, a pretty good side with it. So yeah, right. So just kind of very kind of high level view. So let's each of these on the left are each of the studies that were included in each arm of this trial. You've got the two groups here. This is just kind of the descriptions of events in each study. So for example, the first one, it's the authors, the journal, the year of publication, the number of events, that is the number of deaths experienced in this first group out of a total of 60 patients. In group 2, they've got 14 deaths out of 51 patients. As Patrick was saying, the square represents the study's effect estimate. So what the study thinks what this individual study thinks the hazard ratio is for this treatment. The size of the square correlates with the number of patients included in the study. So for example, this last study here, Thurs et al. The box is quite large, so that's got more patients in it than the first one. The line is not so much the standard deviation, but it's more the confidence interval of the estimate. And the middle line is kind of the line of, I think it's called the line of unity or something. It's the line where there's kind of no difference in treatment, no difference in effect based on the intervention that you've got. And here on the right, this is just a summary of the same thing, just in numerical form. So this is saying that the hazard ratio is 0.71, and this is the confidence interval. So this is 0.33, and this is 1.51. And the p-value is whether this result is significant. If this line, the confidence interval for each study, crosses unity, which is going to be 1 in this case, the result is not significant. As you can see here, this line does not cross unity, so the p-value is less than 0.5. Okay, and then so these are the individual studies, and then you have the overall finding of the meta-analysis. So this is what they've done here is extracted all the patient data from these studies and rerun their analysis. And so they found a total. So these numbers should all add up to so the number of deaths here, 81, should equal. It should just be the sum of these numbers in this column. You've got the effect estimate, the total effect estimate, which is 0.64, and they've got a confidence interval that does not cross 1, and a p-value confirms that. So this is kind of the layout of the results from this meta-analysis. So we're going to focus this, as I said, on steroids and control. What is the summary of this kind of analysis? What is this saying? So you're looking at 28-day mortality.
Sorry, go ahead, Christopher.
Oh, well, you can also go ahead, but so you can see that the cutoff value, the central line, and you can see that the overall on the steroid part, it's it's to the left of the midline. So it says that overall that the combined effect of all the studies is that the steroids have a decreased 28-day mortality compared to the control group.
Yeah, exactly. That's exactly it. So as you can see, only one of the individual studies actually showed a true decline. Only one could be said to have a statistically significant decline in mortality because the p-value was less than 0.5. For the others, even though they're quite big studies, they weren't able to reach significance. But here, this shows nicely that when you take all the data together, you will find that there in fact is a reduction in mortality with steroid use, and that is statistically significant. So that is the power of the meta-analysis, because if this fairly big study also failed to find a significance. So you're closer to estimating the truth in a meta-analysis.
And another thing that's really nice about meta-analysis, besides like summarizing the data right in the figure, is just you look at the years of these articles and you have to start thinking about what's your clinical question that you're trying to answer, and then have things change in that period of time, because that's also really fine-tuned looking at these articles separately, because sometimes you don't want to just look at this overall effect, but you kind of want to really fine-tune go into each one, which you're doing when you're reviewing. But as someone who's like not involved with the article whatsoever, when you get the final conclusion, when you look at this plot, you're kind of really looking, another thing that I look at is the years, because I know as time goes on, you're going to feel this, earlier you're talking about Christian and older, but just medicine changes so drastically. And so you want to look at the clinical question as being answered. And if anything's going to be that you're aware, that could be confounders as well that may have not been accounted for.
Yeah. Thanks, Dr. Rosa. Yeah, exactly. So you get a lot of information on these graphs. So what is heterogeneity? Just coming back to this point.
Patrick, you want to give it a shot since you had mentioned the concept to begin with?
You just want me to try say the word again. So, for example, if they tested in one trial, they tested 5 milligrams, and then in another trial they tested 10 milligrams. Any kind of discrepancy between dose, duration. Maybe if the enrollment was like slightly different. All of these small changes, and I guess when you add all these additional trials, they can make changes to the outcome of the effect.
Yeah. Exactly right. So you have it's about comparing like with like, and kind of comparing apples with pears. You have to make sure you are comparing similar enough things that you can actually combine the results of these studies. So you went through some things that can cause heterogeneity. You can kind of divide them into, say, clinical factors, like you were saying, doses, medications, the patient population. You can also include. You can divide them into methodological factors, like the design of the studies, the way they were actually administered. And then statistical techniques as well. So there's lots of reasons why any study might be different from the next one, even though they're both trying to answer the same basic question. Some statistics you'll see when you're reading meta-analyses about quantifying heterogeneity. So how much heterogeneity is there? The two key ones that are kind of commonly used are Cochrane's Q, which is just the question, is there strong evidence of heterogeneity in this study? It's kind of a yes/no thing. It's just, is there or is there not? They use a p-value usually of 0.1 rather than 0.5 because partly it's convention, but also you have to be kind of, this isn't a very strong statistical measure, so you kind of allow a bit more kind of leeway. Heterogeneity, in some form, there'll always be heterogeneity in every study, unless it's basically exactly the same trial. Of course, you're going to have differences. So this was quite often going to be positive. So then the next question is, does the amount of heterogeneity matter? So Cochrane's Q is there or is there not heterogeneity? The next statistic is the I-squared statistic, which is how much heterogeneity is there? How much of the variability in effect estimates is due to this between study variation in technique rather than just random chance that you would expect because you've looked at different groups of people. So as I think it was, someone was saying this earlier on, that you kind of, this is a kind of a general guide. This is from the Cochrane collaboration about how much heterogeneity is significant. So generally speaking, 0 to 40% is thought to be sort of not important. And there's grade 75% to 100% is very significant heterogeneity that will materially impact your ability to draw conclusions based on this analysis. So with that in mind, can someone compare the heterogeneity between these two analyses? Which is more heterogeneous? Which is harder to draw a conclusion from?
The answer is inside the big red box that Mantej highlighted.
So the first one, the p-value is above 0.1. So the Q-statistic would say there's not significant heterogeneity, and the I-squared, the two work hand in hand. The I-squared shows you that there's 31% heterogeneity between the studies, which is actually, as we saw earlier, not considered that significant. In this group, the p-value is slightly above 0.1. So the Q-statistic would say there is not, but actually when you look at the I-squared, it's 55%, which is moderate heterogeneity between the studies. So that just means you should interpret this finding with more caution than you should interpret this finding. Okay. The last kind of major thing, we've gone through quite a lot, but the last major thing that is important in the meta-analysis is a sensitivity analysis. So this is how sensitive are your conclusions to small changes in the source evidence. So if you drop one study out, does your whole conclusion change? Or is there a lot of missing data in one study that will again affect your ability to combine them together? So these authors did this. They said that this one RCT, Cabaret et al., didn't have individual level data available that they needed to kind of run their analysis, or it just wasn't accessible in the same way. So then they ran a sensitivity analysis, which is shown here. So in this conclusion, what they've done is run the same analysis, but just dropped all the data from this study out. So this is asking the question, if you drop that one study out, does your whole conclusion change? Does the hazard ratio become non-significant or even sort of harmful? And the answer is no. The hazard ratio is still is 0.63, is protective, and it's still significant. So you could say that this study is robust to kind of small changes in source data. It kind of depends on which study you drop out. If you dropped out the last one, you'd probably have you lose a lot of power, and that would significantly affect your conclusions. I'm going to skip this slide because this is just, so skip it. So let's do forest plot. This is something that, again, people come across when they do meta-analyses. There actually was not a forest plot in the study because they looked at individual level data rather than just looking at aggregates of the studies. Can someone talk me through this? Patrick, you kind of tried the last one. You said this is the kind of the line of unity. You said these are the individual studies. The horizontal lines are the confidence intervals. But what is a diamond?
I can't actually remember.
No, anyone else? Doesn't have to be. What's the diamond here?
Is that the summary effect after you weigh for the individual studies? Yeah,
exactly. So it's a summary effect. So instead of in this diagram, for example, they've got squares here. They're saying this is implying that this is the individual data they've put together into their own kind of final conclusion. If instead of doing that, if you were just to take the estimates of these individual studies, not look at the underlying kind of data, just take the study's conclusions and weight those based on the size of the study, you would express that as a summary effect estimate, and that would be shown as a diamond. So the kind of concept is the same as the previous graph. It just, if it's a diamond, that implies that the authors have just looked at the overall study estimates, not the underlying patient data, and analyzed the data themselves. So just to kind of wrap up, we've kind of whizzed through meta-analysis and the techniques for doing it. Just to bring you back to the conclusion of this paper, with all the kind of stuff we've been through, can anyone sort of basically come to the same conclusion that the authors did? This is the top figure is the effect of steroids on mortality at 28 days, and the bottom figure is the effect of steroids on mortality at 6 months. So what is the conclusion from this study?
Looks like there's only statistical difference after 28 days, but there's no difference after 6 months. Yeah,
exactly. Thank goodness you got that right, because that's very vindicating for me. So yeah, exactly, you've got it right. That's what it is. That the whole point of what they showed after all this work, and is that the only thing that's really significant is that steroids in severe alcoholic hepatitis will reduce 28-day mortality, but have no effect on mortality at 6 months. And so then they're saying, well, therefore we need sort of treatments that will affect the longer term success of treatment of alcoholic hepatitis. And there's lots of reasons for that. Some of them, I think a large part will be the resumption of alcohol intake in most patients with alcoholic hepatitis. So just to summarize, so meta-analysis, so it's a combination of existing studies. You either use summary statistics from the studies and come up with that little funnel plot with a forest plot, sorry, with a diamond, or you look at the individual data from each of the studies and then analyze it yourself and come up with kind of a separate estimate of effect. The strength is totally dependent on the underlying data. If the underlying studies are biased, and they all share the same bias, your meta-analysis is going to have that bias inextricably in it. So it's totally dependent on the data that you have available to you. Some common things to kind of look out for the evidence of publication bias in a meta-analysis. So, well, not so much in the meta-analysis, but is there publication bias in the existing literature that only certain studies are being published? Is there significant heterogeneity in the meta-analysis? So you can use a Q statistic or the I-squared statistic to try and determine that. And then have they done a sensitivity analysis as well? So if you drop one study out, for example, does everything change? And that's that. So any questions about any of that?
I mean, I think you did an excellent job. This is our second of what we're trying to do with changing EBM to kind of focus on specific topics. And I think you did an excellent job. I think the only thing I would throw it out to you guys is, I was the time where we would go to the libraries to go get the articles. And now it's a lot easier to do these meta-analysis because everything's electronic. But I throw it out there, the idea of what's been going on with COVID, with these non-peer-reviewed studies that are available to be able to look at, these MEDI-IRX kind of things that people do look at, and what's going to happen with those, and where are those in these meta-analysis at that point, because these are not ones that are peer-reviewed, so they're not necessarily in journals, but they're being open access for anybody to really look at. So I think that's a question to come, and it's just something to throw out there in terms of like how that's going to be taken into account, and is that really can that be continued here on as a meta-analysis when they're not necessarily published, but really just out there in the netherworld. So, and that's something we talk about a lot in the ID world, just because of COVID and the impact of COVID and some of the changes that we have to make with the treatment guidelines. But you did a really great job, and I'm grateful for the engagement. And yes, I am realizing that one of the things that I had a hard time with EBM was that everyone has a different engagement, but at the same time, what I like about the Zoom world is that we can chat. And so even though I don't want to interrupt you either, we're able to kind of include. So I did put the two of the references. One is one that Rafa found, which is from the JAMA surgery, which is just looking at the core concepts that Mantej was looking at for meta-analysis. And then the second was the Cochrane, which is a nice handbook that has like some more advanced detail for those who want to look into a little bit more. So thank you, everybody. You guys did great. I know we were running late, so